The universe is hiding its greatest secrets in plain sight. We are about to journey through 50 galactic phenomena that defy explanation, stories where the rules of physics break down, and cosmic detective stories hit dead ends. By the end, you will see the night sky not as a static painting, but as a living puzzle box of epic scale. We will encounter a star that dims in ways nothing natural can explain, and listen to a one-time signal from the void that screamed for attention. What do you believe is the universe's most carefully guarded secret? That single, powerful radio burst from the cosmos seemed to shout for just 72 seconds before falling silent forever. It was the evening of August 15, 1977, at the Big Ear Radio Telescope in Ohio, a machine designed to listen to the quiet whispers of the universe. What it heard that night was anything but a whisper. The signal was a focused, narrowband radio wave, a precise frequency that natural cosmic objects almost never produce, and it came from the direction of the constellation Sagittarius. It was so intense, so perfectly aligned with a predicted frequency for interstellar communication, that when astronomer Jerry Amon reviewed the data printout, he simply circled the alphanumeric code representing its strength and wrote one word in the red pen's margin. Wow, that single exclamation gave the phenomenon its immortal name. The signal rose to a peak and then faded away over its brief duration, matching exactly what you would expect from a distant, fixed source as the Earth's rotation carried the telescope's gaze across it. This was not static, not a satellite, not a passing airplane. It was a clean, deliberate-seeming shout from the void. Yet, in the decades since, despite countless attempts to find it again, the sky from that precise point has remained utterly, stubbornly silent. Was it a one-time cosmic event, some freak natural emission we still do not understand? Or was it a fleeting message, a cosmic beacon that flickered on just long enough to capture our attention before vanishing back into the dark? The wow signal endures not because we solved it, but because it was perfect. It was exactly what we were listening for, and it has never repeated. It stands as a ghost in the machine of astronomy, a reminder that sometimes the most profound answers are the ones we only hear once. That ghostly signal fades into a far deeper and more pervasive cosmic silence. Our second galactic mystery is not a fleeting event, but a permanent, invisible presence. It is the universe's most dominant ghost, a substance that sculpts the cosmos yet refuses to be seen. We call it dark matter. You cannot touch it, you cannot see it with any telescope we have ever built, but we know it is there because of the immense gravitational hand it places on everything we can observe. It is the hidden architecture, the invisible scaffolding upon which the entire visible universe is built, making up roughly 27% of all the mass and energy in existence. The story of its discovery begins not with seeing something, but with noticing that the math did not add up. In the 1930s, a brilliant and often contentious astronomer named Fritz Zwicky was studying a gigantic swarm of galaxies known as the Coma Cluster. He measured how fast these galaxies were whirling around the cluster's center, and he made a startling calculation. The galaxies were moving so incredibly fast that the combined gravitational pull of all the stars, gas, and dust he could see should have been utterly insufficient to hold the cluster together. By all rights, the entire swarm should have flown apart, its member galaxies scattered into the void. The only logical explanation was that there was far more mass there than anyone could see, a vast halo of something dark and heavy providing the extra gravity to keep the cosmic city from exploding. Zwicky called it Dunkel Materie, dark matter. For decades, this was considered a curious anomaly, but later observations of how individual galaxies spin sealed the case. Stars on the outer edges of spiral galaxies orbit just as fast as those near the center, which defies the laws of gravity as we understand them, unless those galaxies are embedded within a massive, invisible sphere of matter. So what is this ghost? The leading candidates are particles that barely interact with normal matter except through gravity. One prime suspect is the WIMP, a weakly interacting massive particle. Think of trillions of these particles streaming through your body every second, as intangible as a breeze through a screen door. Another candidate is the Action, a hypothetical particle so incredibly light it seems absurd it could have such weighty consequences, but in vast numbers it could account for the missing mass. The hunt for these phantoms is a story of extraordinary patience and engineering. Scientists have built ultra-sensitive detectors a mile deep in abandoned mines, shielded from cosmic rays by a mountain of rock, waiting for the once-in-a-lifetime tremor that might be a dark matter particle bumping into an atom of xenon or germanium. Others look to space, where telescopes scan for indirect signals, like the faint glow that might be produced if dark matter particles annihilate each other. After nearly a century, we have mapped the shadow of this ghost in exquisite detail. We have charted its distribution across the cosmos, yet its true identity remains one of the greatest unsolved puzzles in all of science. We live in a universe dominated by something we cannot perceive, a silent partner in the cosmic dance whose steps we can only infer from the movements of others. But if dark matter is the universe's unseen ghost, dark energy is its phantom force, an active and dominant power reshaping cosmic destiny. The discovery of dark energy was not a gradual realization but a profound shock to the scientific world in the late 1990s. Two independent teams of astronomers were using distant stellar explosions, supernova, as cosmic mile markers to measure how fast the universe was expanding. They expected to find that the gravitational pull of all the matter in the cosmos was gradually slowing this expansion down, like a ball tossed upward slowing as it reaches its peak. What they found was the exact opposite. The most distant supernova were dimmer than they should have been, meaning they were farther away than anyone predicted. The expansion of the universe was not slowing down, it was speeding up. Some invisible, repulsive force was pushing galaxies apart from one another at an ever-increasing rate. This revelation was so monumental it earned the team leaders the Nobel Prize in Physics in 2011. We now call that force dark energy. The numbers are staggering. While dark matter makes up about 27% of the universe, dark energy is estimated to be a colossal 68% of the total energy content of the cosmos. Everything we can see and touch, every star, every planet, every human being, constitutes less than 5% of reality. The rest is these two profound mysteries. So what could this phantom force possibly be? The leading and simplest explanation is that dark energy is a property of empty space itself. In Einstein's equations, this concept is called the cosmological constant, a kind of innate energy woven into the fabric of the vacuum. Think of empty space not as truly empty, but as a seething foam of virtual particles that flicker in and out of existence, generating a constant, gentle outward pressure. This pressure is negligible on small scales, but across the vast, empty gulfs between galaxy clusters, it adds up to become the most powerful force in the universe. The implications of this acceleration are both beautiful and chilling for the ultimate fate of everything. If dark energy continues to dominate, the expansion will accelerate forever. Distant galaxies will eventually be pushed away so fast their light can never reach us again. The observable universe will shrink to our local galactic neighborhood. Over trillions of years, star formation will cease, stars will burn out, and the cosmos will become a cold, dark, and profoundly lonely place, a scenario cosmologists call the Big Freeze or heat death. We are left with a universe where the dominant forces are not the light and heat of stars, but the silent push of empty space and the invisible pull of unseen matter. While dark energy pushes the cosmos apart on the grandest scale, a single, unassuming star over 1,000 light-years away is doing something just as strange on a much more intimate stage. This is Tabby's star, a sun in the constellation Cygnus that behaves like no other star we have ever seen. Its official designation is KIC 8462852, but it is named for the astronomer who led its investigation, Tabitha Boyajian. Its story begins not with a professional astronomer's targeted search, but with the collective curiosity of the public. The Kepler Space Telescope was designed to find planets by staring at stars and waiting for the tiny, periodic dips in brightness caused by a world passing in front of it. The data from Kepler was so vast that scientists enlisted volunteers through the Planet Hunters project to help scan the light curves, looking for patterns that automated algorithms might miss. In 2015, this citizen science army flagged a star that was not just blinking, but flickering in a profoundly bizarre way. Most planet transits cause a star to dim by less than 1%. Tabby's star, however, experienced sudden, dramatic drops in brightness of up to 22%, and these dips were not regular or symmetrical. They were jagged, unpredictable, and staggeringly deep. Imagine looking at a 100-watt light bulb and watching it, without warning, dim to the brightness of a 78-watt bulb, then flicker erratically before slowly returning to normal. No known planet could cast a shadow that large, and the irregular shape ruled out a simple, clean orbital transit. The initial, most natural explanation was a colossal swarm of comets, thousands of them, breaking apart and creating a vast, uneven cloud of dust and ice that would intermittently block the star's light. But the scale required was almost unimaginable, a level of cometary activity never before witnessed around any star. This is when the more speculative and thrilling idea entered the public imagination. Could this be evidence of alien engineering, specifically the construction of a Dyson sphere, a hypothetical megastructure built by an advanced civilization to capture a star's entire energy output? The irregular dimming patterns could, in theory, be caused by partially constructed swarms of giant solar collectors orbiting in a chaotic array. The scientific community, while skeptical, took the mystery seriously and pointed every available telescope toward Tabby's star, from radio dishes listening for artificial signals to instruments measuring every wavelength of light. These follow-up observations have painted a more complex but no less puzzling picture. The star's light is dimmed more in some colors than others, which strongly suggests the blocking material is made of dust, not solid panels. This seemed to support the comet swarm idea, but then another layer of the mystery emerged. When astronomers looked at historical photographic plates of the star's region going back over a century, they found that Tabby's star has also been undergoing a long-term, gradual dimming. Over the past 100 years, its overall brightness has faded by a significant amount. A swarm of comets might explain short-term dips, but not a century-long fade. Other theories have since been proposed. Perhaps the star recently devoured a planet, creating a temporary debris field. Or maybe it is surrounded by a warped, dusty ring system from a catastrophic collision of moons. Yet, each explanation struggles to fit all the data perfectly. Tabby's star remains an enigma, a cosmic detective story where every clue seems to lead to a new question. It is a powerful reminder that sometimes the most profound discoveries are not answers, but better, more precise ways of asking why. The mystery of a single, flickering star pales before a cosmic event that unleashes the energy of 500 suns in less time than it takes to blink. These are fast radio bursts, or FRB, and their discovery rewrote the book on how violently the universe can shout. The story begins not with a real-time observation, but with a detective digging through old case files. In 2007, astronomer Duncan Lorimer was reviewing archival data from the Parkes Radio Telescope in Australia, searching for distant pulsars. Buried in the recordings from 6 years prior, he found something astonishing, a spike of radio waves so intense it saturated the detector. It lasted a mere 5 milliseconds. In that fleeting instant, it released more energy than our sun emits in 80 years. For a long time, this lone event, now called the Lorimer burst, was considered a possible fluke, a glitch in the telescope, or a local source of interference. But then more were found. Astronomers realized the sky was peppered with these incredibly brief, incredibly powerful explosions, each one a brilliant, mysterious flash in the cosmic dark. The hunt was on to catch one in the act and trace it back to its source. The breakthrough came with FRB 121102. Discovered in 2012, this burst did the unthinkable, it repeated. Unlike the one-off events, this source in the constellation Auriga flashed again and again in an unpredictable pattern. This repetition was the key that finally unlocked a location. By training a network of the world's most sensitive radio telescopes on the area, scientists were able to pinpoint the bursts to a startling place, a tiny, faint dwarf galaxy over 3 billion light-years away. That distance confirmed the mind-bending power of these events. To be visible across such a vast gulf, they must be truly cataclysmic. So what cosmic engine can possibly produce such a concentrated, titanic blast? The prime suspect is a magnetar, an intensely magnetic type of neutron star, the collapsed core of a giant star. A magnetar's magnetic field is 1,000 trillion times stronger than Earth. Theorists suggest a starquake on the surface of such a monster, a sudden cracking of its rigid crust, could unleash a magnetic shockwave powerful enough to blast out a fast radio burst. Another idea involves a magnetar being engulfed by the disk of material around a black hole, creating chaotic and repeated eruptions. Yet, the sheer diversity of FRBs, with some repeating and others silent, suggests we might be looking at more than one kind of source. More exotic theories, while less likely, capture the imagination. Could they be produced by the violent snapping of cosmic strings, hypothetical defects in the fabric of spacetime? Or, given their precise, bright nature, could they be evidence of advanced technology, like powerful interstellar beacons or the signatures of light-sail propulsion systems? While natural explanations are far more probable, the extreme and fleeting nature of FRBs forces astronomers to consider every possibility. Today, new telescopes like the CHIME array in Canada are discovering them by the dozens, mapping a hidden landscape of millisecond violence across the cosmos. Each one is a postcard from a distant, turbulent event, written in a language of raw energy we are only just beginning to translate. That millisecond flash of radio energy is a scream from the distant universe, but there is a quieter, more persistent pull much closer to home, a force guiding our entire galactic neighborhood on a journey we cannot see. All the galaxies around us, including our own Milky Way, are not drifting aimlessly through the void. They are flowing like leaves caught in a gentle but immense river current toward a specific point in the cosmos. Astronomers call this destination the Great Attractor. The discovery of this mysterious pull began with a simple observation of galactic motion. In the 1970s, scientists mapping the universe expected to see galaxies moving apart from each other in the smooth, uniform expansion described by Edwin Hubble. But when they looked closely at the motions of galaxies in our local region, they noticed something was off. Our Milky Way and its neighbors were all streaming in the same direction at a speed of over 600 kilometers per second, a velocity far greater than the general expansion of space could account for. It was as if every galaxy in our local supercluster had received the same silent command, all moving toward a point in the sky near the constellations Centaurus and Norma. Something with truly colossal gravity was pulling us in. Identifying exactly what that something is, however, presented a monumental problem. The direction of the Great Attractor lies directly behind the plane of our own galaxy, a region astronomers poetically call the zone of avoidance. Imagine trying to see a distant city by looking through the densest part of a fog bank. That is what the zone of avoidance is like, a thick band of cosmic dust, gas, and billions of stars from the Milky Way spiral arms that completely blocks our optical view. For decades, the Great Attractor was a gravitational ghost, its presence felt but its face completely hidden. The key to piercing this veil was to use telescopes that see in wavelengths other than visible light. Radio telescopes and X-ray observatories, which can peer through the interstellar dust, began to map the hidden landscape. What they revealed was not a single, monstrous object, but an immense concentration of mass, a gravitational focal point where several rich galaxy clusters, like the Norma cluster, have gathered together. This region, now estimated to contain the mass of tens of thousands of Milky Way galaxies, acts as the downtown core of our local cosmic metropolis. The primary engine of its gravity is likely the same unseen force we discussed earlier, dark matter, woven through and between the visible galaxies in a dense, invisible web. This discovery also provided a crucial piece of a much larger puzzle, redefining our cosmic address. The Great Attractor is not the end of the line, but merely a major waypoint. We now understand it as the central gravitational anchor of an even vaster structure, a supercluster of galaxies 100,000 times more massive than the Milky Way. In 2014, astronomers gave this immense network a beautiful Hawaiian name, Laniakea, meaning immense heaven. Within Laniakea, every galaxy, including our own, is flowing along filamentary pathways toward the Great Attractor, like water droplets in a river system, all draining toward a central basin. So we are on a journey, pulled by the hidden architecture of the universe toward a point we once could not see. A reminder that even on the grandest scales, we are not still, but passengers on a slow cosmic current. That cosmic current pulling us toward the Great Attractor operates on a scale of billions of years, a time span that makes the entire history of humanity feel like a fleeting instant. And within that immense stretch of cosmic time lies a question so profound it redefines our loneliness. The universe is staggeringly vast and unimaginably old, with hundreds of billions of galaxies, each containing hundreds of billions of stars. The raw numbers suggest that planets like Earth should be common, and that life, even intelligent life, should have arisen many times over. So, with all that potential, the night sky should be ablaze with signals crisscrossed by the traffic of civilizations. Yet, we hear only silence. This glaring contradiction is the heart of the Fermi paradox, named for the brilliant physicist Enrico Fermi, who, during a casual lunch conversation in 1950, posed the deceptively simple question, where is everybody? The logic is compelling. Our galaxy, the Milky Way, is about 13.6 billion years old. Our Sun is a relatively young 4.6 billion years old. That means there were billions of years before our solar system even formed for other stars and planets to arise and for life to evolve into intelligence far older and more advanced than our own. Even at the slow pace of interstellar travel, a civilization with a modest head start of just a few million years should have had ample time to colonize or at least explore the entire galaxy. The evidence of their existence should be everywhere. To quantify this hope, astronomer Frank Drake crafted an equation, not to find an answer but to frame the debate. The Drake equation multiplies a series of probabilities: the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction where life actually emerges, the fraction where life becomes intelligent, the fraction that develops technology to communicate, and finally, the length of time such civilizations release detectable signals into space. Plug in optimistic numbers and you get a galaxy teeming with communicative civilizations. Plug in more conservative estimates and the number can shrink to just a handful or even just us. But the paradox persists because even a handful should, over cosmic time, make their presence known. The solutions proposed to this great silence range from the sobering to the terrifying. Perhaps the most chilling idea is the concept of the Great Filter. This theory suggests that somewhere between the emergence of life and the development of a galaxy-spanning civilization, there is a catastrophic barrier, a step so difficult that almost every species fails to pass it. The haunting question is, where is this filter located? Is it behind us, meaning the jump from simple life to complex, multicellular life is extraordinarily rare, and we are a miraculous fluke, or is it ahead of us, waiting in our future? This would mean that the development of advanced technology inevitably leads to self-destruction through nuclear war, engineered pandemics, or environmental collapse. Our current technological adolescence, then, would be the most dangerous phase in a civilization's existence. Other explanations are less apocalyptic but equally mind-bending. Perhaps intelligent life is common, but it quickly evolves beyond the need for the crude radio signals we are listening for, moving to technologies we cannot yet conceive or detect. Maybe they are out there, but they have chosen to remain hidden, observing younger species like us in a cosmic zoo, adhering to a strict policy of non-interference. Or the universe might be a much more dangerous place than we realize, with predatory civilizations that silence others before they become a threat, leading everyone to maintain radio silence for safety. There is also the humbling possibility that we are simply too early. If life on Earth is among the first to reach this stage in a universe that is only now becoming habitable for the long term, then others may be just beginning their journey or are still billions of years away from arising. The Fermi paradox holds up a mirror to humanity, forcing us to confront our own fragility and future. That profound silence is not just an astronomical curiosity. It is the backdrop against which we must write our own story, wondering if we are the first chapter, the last, or something in between. The profound silence of the cosmos makes every signal we do detect feel monumental, but sometimes the most telling messages come not from the stars but from our own machines as they leave home. Two human-made ambassadors, the Pioneer 10 and Pioneer 11 spacecraft, carried with them a tiny, stubborn mystery for over 30 years. After completing their historic missions to Jupiter and Saturn, these twin probes sailed into the dark, becoming the first human objects on a trajectory to leave our solar system entirely. As they journeyed outward, scientists tracking their radio signals noticed something deeply puzzling. Both spacecraft were slowing down ever so slightly, more than the known laws of gravity could account for. The drift was minuscule, a deceleration of about 1/10,000,000th of a gravity on Earth, equivalent to the gentle pressure of a single sheet of paper resting on your hand. Yet, over the vast distances and decades of travel, this tiny anomaly added up, pulling the Pioneers hundreds of kilometers off their predicted courses. This was the Pioneer anomaly, a ghostly tug that seemed to defy explanation. For years, it was measured with exquisite precision through the Doppler shift of their radio signals, the same principle that makes a siren's pitch change as it passes you. As the probes sped away, their radio frequencies should have shifted in a predictable, slowing pattern due to the sun's gravity. Instead, the shift was just a little bit more, as if an invisible hand was applying a constant, gentle brake. This persistent drift sparked a firestorm of speculation. Could it be evidence of new physics, a flaw in Einstein's theory of gravity on the largest scales? Perhaps it was a hint of dark matter's local influence or an unknown property of space itself. The anomaly was so small, yet so consistent, it became a tantalizing loose thread in the fabric of our understanding. Unraveling it required a Herculean effort of cosmic detective work. Teams of scientists spent years diving into decades-old engineering documents, reconstructing the thermal and electrical profiles of the long silent probes. They built intricate computer models simulating every conceivable force, from the subtle pressure of the solar wind to the gravitational pull of undiscovered asteroids. The breakthrough came not from looking outward into the cosmos, but from looking inward at the spacecraft's own design. The Pioneers were powered by radioactive thermoelectric generators, which produced electricity from the heat of decaying plutonium. This heat had to be radiated away into space to keep the instruments functioning. The spacecraft were asymmetric, with their large radio dish antennas pointed back at Earth, acting like a giant reflector. The team's meticulous modeling revealed that this heat radiation, emitted unevenly from the craft's body, was not perfectly balanced. A tiny fraction more heat was radiating from the back of the spacecraft than from the front. This created an immeasurably small but constant photon pressure, a gentle push of infrared light itself, acting like a microscopic rocket thruster pointed back toward the sun. It was this thermal recoil force, the spacecraft essentially pushing against its own warmth, that accounted for almost all of the anomalous deceleration. The Pioneer anomaly stands as a monument to scientific rigor, a story where the most exotic explanations gave way to a profoundly mundane yet brilliant piece of engineering physics. It reminds us that the universe often whispers its secrets in the language of imperceptible details, and that sometimes the key to unlocking a cosmic mystery is found not in the distant void, but in the quiet glow of our own creations. That phantom tug on the Pioneer probes was a mystery solved by looking inward, but a few years later, an object from the farthest reaches of space gave us no such chance for a second look. In October 2017, the Pan-STARRS telescope in Hawaii spotted a faint point of light moving at breathtaking speed. Its trajectory was the giveaway, a steep, hyperbolic path that meant it was not from our neighborhood. This was our solar system's first confirmed interstellar visitor, a cosmic tourist passing through on its way from somewhere else to somewhere else. Astronomers named it Oumuamua, a Hawaiian word meaning scout or messenger from the distant past. What we learned in the frantic weeks as it sped away from the sun only deepened the mystery. First, its shape. By measuring how its brightness changed dramatically as it tumbled, scientists deduced it was not round like a typical asteroid or comet. It was extraordinarily elongated, perhaps 10 times as long as it was wide, shaped like a cigar or a flat pancake. No natural object we had ever seen looked quite like it. Second, it showed no visible coma, the fuzzy cloud of gas and dust that surrounds a comet when sunlight warms its icy surface. This suggested it was a dry, rocky asteroid. But then came the third and most perplexing clue, its motion. As Oumuamua swung around the sun and began its exit from the solar system, it accelerated slightly in a way that pure gravity could not explain. This non-gravitational acceleration is exactly what comets do, as jets of vaporizing ice act like tiny rocket thrusters, yet no such jets or surrounding dust were ever detected. It was as if an invisible engine was giving it a gentle, steady push. The scientific scramble to explain these conflicting facts produced a cascade of theories. Could it be a rare type of comet after all, one with a very unusual composition? One idea proposed it was a hydrogen iceberg, a chunk of solid molecular hydrogen that would vent gas invisibly as it warmed. Another suggested it was a nitrogen iceberg, chipped off a Pluto-like world in a distant star system. But each of these exotic natural explanations struggled to fit all the data perfectly. The strangeness of the object led Harvard astronomer Avi Loeb to propose a more sensational possibility, that Oumuamua could be artificial debris from an advanced civilization, specifically a discarded light sail. A light sail is a proposed spacecraft that uses the gentle pressure of sunlight for propulsion, much like a boat's sail uses wind. Loeb argued that the object's flat shape, its unusual brightness, and its precise non-gravitational acceleration could be consistent with a thin, reflective sheet of material being pushed by starlight. The scientific community largely finds this unlikely, emphasizing that extraordinary claims require extraordinary evidence, and natural explanations, however novel, are always preferred. Yet the core truth remains: Oumuamua defied easy categorization. By the time we noticed it, it was already leaving, and we had no time to send a probe or get a closer look. It is now just a faint, speeding dot far beyond the orbit of Neptune, receding into the interstellar dark forever. it leaves behind a profound legacy, not of answers but of possibility. Its visit proved that interstellar objects are real and likely common, and it forced us to confront how little we understand about the geology of other star systems. Was it a bizarrely shaped rock, a shard of exotic ice, or something else entirely? That first scout from the Great Dark did not tell us. It simply delivered its message of mystery and sailed on. Oumuamua's fleeting passage was a reminder of how much lies beyond our solar system, but a profound boundary exists much closer to home, a frontier marked not by a wall, but by a sudden and unexplained emptiness. Out beyond the orbit of Neptune, the sun's light grows weak and cold, and here lies the Kuiper Belt, a vast donut-shaped region of frozen leftovers from the solar system's birth. This is the home of dwarf planets like Pluto, Haumea, and Makemake, and countless smaller icy bodies. For decades, astronomers expected this belt of debris to extend smoothly outward, gradually thinning as it merged with the even more distant Oort cloud. But when powerful surveys like the one conducted by the Subaru telescope began to map this distant realm in detail, they found something startling. The population of Kuiper Belt objects does not fade away gently. Instead, it hits a cliff at a distance of roughly 50 astronomical units from the Sun, about where Pluto orbits. The number of detectable objects is as predicted. But just a little farther out, beyond about 55 astronomical units, the population of objects drops off a precipice. It is as if someone drew a cosmic line in the sand and said, "Nothing beyond this point." This is the Kuiper Belt Cliff, and its existence defies our basic models of how the solar system formed. The primordial disk of gas and dust that swirled around our infant sun should have distributed material much farther out. So what carved this abrupt edge in our own backyard? One compelling theory points the finger at gravity, but not from anything we can currently see. The hypothetical planet 9, a world perhaps 5 to 10 times the mass of Earth thought to orbit far beyond Pluto, could be the architect. In this scenario, Planet 9's immense gravitational influence over billions of years could have acted like a cosmic shepherd, clearing out the region just beyond its own orbit. It might have flung some objects into wildly tilted orbits we have not yet surveyed, or ejected others from the solar system entirely, leaving behind this stark vacancy. Another possibility looks back to the very beginning. Perhaps the protoplanetary disk itself had a sharp outer edge, cut off abruptly by a stellar neighbor's gravitational influence, or because the cloud of material from which our sun formed was simply finite and dense only out to a certain radius. This would mean the Kuiper Belt Cliff is a fossil, a permanent imprint of the solar system's birth conditions. There is also a more subtle, observational explanation. Could it be that objects beyond the cliff are simply too dark for our telescopes to see? As you go farther from the sun, temperatures plummet, and different, less reflective ices might dominate, making these distant bodies incredibly faint. Or perhaps their orbits are so stretched and elongated that they spend most of their time far beyond the cliff, only swinging inward briefly and rarely, making them nearly impossible to census. The Kuiper Belt Cliff is a quiet mystery, a puzzle written in absence. Solving it requires us to look for what is not there, and to question whether the missing pieces are hidden in the dark or were never there at all. The Kuiper Belt Cliff is a boundary defined by absence, a place where expected objects simply vanish. But in the vast ocean of galaxies, astronomers have found an island that is missing something even more fundamental. The very ghost we believe holds the universe together. This is NGC 1052DF2, a galaxy that appears to defy the most basic rule of modern cosmology. It is a galaxy seemingly without dark matter. Discovered in 2018, this object is a member of a class called ultra-diffuse galaxies. These are ghostly, wispy collections of stars, so faint and spread out you can practically see right through them. NGC 1052DF2 is so ethereal that individual distant galaxies are visible behind it, as if it were a cosmic scrim. But its true strangeness was not in its faintness, but in the behavior of the 10 bright globular clusters, dense balls of ancient stars that orbit it. By measuring the speeds of these clusters, astronomers could calculate the total mass of the galaxy pulling on them. The result was a shock. The clusters were moving surprisingly slowly. When the scientists added up the mass of all the visible stars in the galaxy, it almost exactly accounted for the gravity needed to produce those sedate motions. There was no room left for the immense invisible halo of dark matter that surrounds every other galaxy of its size we have ever studied. It was like watching a handful of pebbles orbit a paperweight, with the motion perfectly explained by the paperweight's own heft, no hidden magnets required. The implications sent tremors through astrophysics. For decades, dark matter has been the central pillar of our model of the universe, the unseen glue essential for galaxy formation. The very existence of a galaxy without it was akin to finding a skyscraper built without a steel frame, standing tall against all engineering principles. Could this single, ghostly object disprove dark matter entirely? Some suggested it might be evidence for modified theories of gravity like MUND, which attempt to explain galactic rotations without invoking invisible particles. But for most scientists, NGC 1052DF2 is not a death knell for dark matter, but a fascinating and bizarre outlier, a clue to a more complex story of how galaxies live and die. The leading explanation is one of cosmic violence. This wispy galaxy resides near a massive elliptical galaxy called NGC 1052. Astronomers theorize that in the distant past, it may have been a more typical, dark matter-rich dwarf galaxy that had a catastrophic encounter with its giant neighbor. During a close pass, the immense gravitational tides could have ripped away not only stars and gas, but also, through a complex process, the loosely bound dark matter halo that once enveloped it. What remained was the stripped-down, diffuse core of stars we see today, a galactic ghost ship sailing on after losing its phantom crew. Another possibility is that it formed in a unique way, perhaps from gas that was blown out during a titanic collision between two larger galaxies, gas that later coalesced into stars without the accompanying dark matter scaffolding. NGC 1052DF2 forces a profound question. Is dark matter an inseparable part of a galaxy's body, or is it more like a garment that can, under extreme circumstances, be torn away? This single, puzzling smudge of light reminds us that for every cosmic rule we think we have uncovered, the universe is always waiting to show us the exception. A galaxy stripped of its dark matter is a cosmic anomaly, but there are places in the universe where the fundamental laws of physics themselves seem to break down completely. This is the domain of the black hole, and at its heart lies a paradox that threatens to unravel our understanding of reality. The conflict is stark and simple. According to the unshakable rules of quantum mechanics, information can never be truly destroyed. If you burn a book, the ash and smoke still contain, in principle, a complete record of every word, every letter, encoded in the arrangement of its particles. The information is scrambled, but it is not gone. Yet, according to Einstein's theory of general relativity, a black hole presents the ultimate dead end. Its event horizon is a point of no return, a one-way street from which nothing, not even light, can escape. If you throw that same book into a black hole, general relativity says it is gone forever, its information lost to the universe, erased from existence. These two foundational pillars of modern physics give us two completely contradictory answers. This is the black hole information paradox, the paradox sharpened into a crisis thanks to the work of Stephen Hawking. In the 1970s, Hawking made a startling theoretical discovery. Black holes are not completely black. Due to strange quantum effects occurring right at the event horizon, black holes should slowly emit a faint glow of particles, now called Hawking radiation. This radiation carries energy away from the black hole, causing it to lose mass and over unimaginable eons evaporate completely. Hawking's initial calculations suggested this radiation was purely thermal, a form of random noise. It contained no information about what had fallen in. So, picture the final stages of an evaporating black hole. It shrinks to a point and vanishes in a final puff of Hawking radiation. According to this picture, every star, every planet, every book that ever crossed its horizon is gone, and all that remains is that featureless thermal glow. The information is not just trapped, it is permanently deleted from the cosmic ledger. This conclusion horrified many physicists as it violated a core quantum principle. The search for a solution has driven theoretical physics for decades, leading to some of the most mind-bending ideas ever conceived. One leading candidate is the holographic principle. This idea suggests that all the information about everything that falls into a black hole is not lost inside, but is instead encoded on its event horizon, the two-dimensional surface that shrouds it. Think of it like a cosmic thumb drive. The three-dimensional interior of the black hole, with all its complexity, is actually projected from information painted on its two-dimensional boundary. Much like a hologram on your credit card creates the illusion of depth from a flat surface. In this view, when the black hole evaporates, that information on the surface is somehow transferred to the outgoing Hawking radiation, preserving it. Another, more violent proposal is the black hole firewall. This theory suggests that the event horizon is not a smooth, uneventful gateway, but a searing wall of ultra-high energy particles. An astronaut crossing the horizon would be incinerated instantly. This firewall would prevent information from ever actually entering the black hole in the first place, resolving the paradox by making the interior irrelevant. But it creates new problems by violating the principle that crossing the horizon should be uneventful. This is not just an abstract debate. The information paradox is the central battlefield in the quest for a theory of everything, a way to marry the quantum world of the very small with the gravitational world of the very large. It forces us to ask what reality truly is, and whether space and time, as we experience them, are fundamental or merely emergent illusions from a deeper layer of information. The fate of a single bit of data falling into a black hole may hold the key to the universe's ultimate operating system. The battle to save information from a black hole's grip forces us to question the very fabric of reality. But what if the universe's oldest photograph already contains a flaw in its background? The faint, cold light that fills every corner of space is not just empty darkness, it is the cosmic microwave background radiation, the cooled and stretched afterglow of the Big Bang itself. This ancient glow is the ultimate baby picture of the universe, taken when it was just 380,000 years old, a snapshot of a hot, dense plasma finally becoming transparent. For decades, this cosmic backdrop has been the cornerstone of modern cosmology, a nearly perfect blackbody spectrum that confirms our basic story of an expanding, homogeneous universe. Maps of its tiny temperature fluctuations, minute variations of 1 part in 100,000, show a beautiful, random speckle pattern. These speckles are the seeds of all future structure, the gravitational blueprints from which galaxies and clusters would eventually grow. According to our most cherished principle, the cosmological principle, the universe on large scales should have no preferred direction or special place. It should be isotropic, meaning it looks the same in every direction. The pattern of hot and cold spots in the CMB should therefore be just that, a random, statistically uniform distribution, like the static on an old television screen. But when scientists began creating exquisitely detailed full sky maps using satellites like WMAP and later Planck, they noticed something that sent a chill down the spine of cosmology. The fluctuations were not completely random. there appeared to be a strange, large-scale alignment, a curious correlation between the hot and cold spots that seemed to line up with the plane of our own solar system, the ecliptic. Even more unsettling, this alignment also appeared to point in a specific direction toward the constellations Leo and Virgo. Astronomers with a dark sense of humor gave this unsettling correlation a dramatic name, the axis of evil. The name is fitting, for if true, it suggests a cosmic preferred direction, a fundamental lopsidedness that contradicts the foundational assumption of isotropy. It is as if you took that baby picture of the universe and found a faint, ghostly arrow pointing directly back at the camera, implying the photographer was part of the scene all along. The implications are profound. Is our entire observable universe somehow special or aligned with our local geometry in a way that defies chance? Could it be that the vast cosmos has a subtle grain to it, like wood, with properties that differ along different axes? The most conservative explanation is that it is simply a statistical fluke. When you analyze a vast amount of data, you can sometimes find patterns that look significant but are just random noise, a cosmic mirage. Another possibility is that it is not a feature of the universe, but a contamination from our own backyard. Perhaps emissions from within our solar system, dust in the Milky Way, or even subtle errors in how the satellite data was processed and cleaned are imprinting this false signal. Teams have spent years trying to eliminate these local effects, and while some features have been reduced, the strange alignments have stubbornly persisted in the data. If it is not an illusion, then the axis of evil represents a genuine crack in the standard model of cosmology. It might point to something exotic happening in the very early universe, perhaps a pre-Big Bang structure or a violation of Einstein's relativity on the largest scales. Some theorists have even suggested it could be evidence that our universe collided with another bubble universe in the multiverse during its inflationary phase, leaving a bruise on the sky. For now, the axis of evil remains an unsolved anomaly, a whisper from the oldest light that we might not be seeing a perfectly random cosmos, but one with a faint, mysterious orientation. It asks us whether the universe truly has no center and no edge, or if we are, against all odds, sitting in a privileged seat. That faint, mysterious axis in the cosmic background speaks of a universe that might be fundamentally lopsided, but in the constellation Monoceros, there is a structure of such precise symmetry it looks like a carefully crafted piece of celestial art. The Red Rectangle Nebula is one of the most geometrically perfect objects ever discovered in deep space. From our vantage point, it appears as a stunning, glowing red X, its four beams connected by what seem to be evenly spaced horizontal bars, forming a cosmic ladder reaching into the dark. This is not an artist's rendering or a trick of the lens. It is a real nebula, a vast cloud of gas and dust illuminated by a dying star at its core, located about 2,300 light-years away. The star, known as HD 44179, is actually a close binary system, two stars locked in a tight orbital dance. As these stars age, they are shedding their outer layers into space, but they are not doing so in a chaotic, explosive puff. Instead, they are ejecting material in two opposing cones, like twin hourglasses placed tip to tip. Our view from Earth looks directly down the barrel of one of these cones, and the dense ring of dust that encircles the star system's waist pinches the outflow, sculpting the cone's edges into the two distinct, diverging beams of the X. The haunting rungs of the ladder, those perfectly spaced horizontal bars, are believed to be caused by a series of concentric dust rings. Imagine the central binary system puffing out material in periodic bursts, perhaps every few hundred years, creating expanding shells of debris. As the bipolar outflow rams through these pre-existing shells, it lights them up at the points of contact, creating the illusion of discrete steps on a glowing staircase. The rich red color comes from a specific type of emission, known as extended red emission, likely caused by ultraviolet light from the hot central stars exciting complex carbon molecules in the dust. What makes the red rectangle so captivating is not just its beauty, but its precision. Nature is often messy, prone to asymmetry and turbulence, yet here we see a structure of near mathematical regularity emerging from the complex, chaotic process of stellar death. It shows that under the right conditions, the simple physics of orbital motion, periodic ejection, and line-of-sight perspective can conspire to create a masterpiece. The exact timing and mechanism that synchronize the binary stars' mass loss to produce such clean, periodic rings remain a topic of active research. This cosmic artwork is temporary, a fleeting phase in the star's evolution. In a few thousand years, the central core will heat up further, ionizing the expelled gas and transforming the red rectangle into a fully fledged planetary nebula, erasing its iconic geometry forever. For now, it stands as a profound reminder that the universe is not only a place of violent explosions and dark mysteries, but also one of breathtaking, delicate structure, where natural processes can write poetry in gas and dust. That delicate geometry of the red rectangle is a temporary masterpiece, but our own galaxy is part of a far grander and more permanent work of art, one being painted on a canvas of billions of years. Our Milky Way is not an island drifting in solitude. It is on a collision course with the largest galaxy in our local group, the magnificent Andromeda Galaxy. This is not speculation or theory. It is a measured, inescapable fact of our cosmic future. For decades, astronomers debated whether the faint blue shift in Andromeda's light meant it was moving toward us or if it was just a local motion within our group. The definitive answer came from the Hubble Space Telescope, which spent years painstakingly measuring the sideways motion of Andromeda against distant background quasars. By combining this transverse velocity with its approach speed, scientists could plot its true trajectory through space with unprecedented precision. The conclusion was stunning. Andromeda is not on a glancing path. It is headed almost directly for the heart of our galaxy. In approximately 4.5 billion years, the two great spiral galaxies will begin their first close pass, initiating a gravitational dance that will reshape the night sky forever. What will this cosmic merger actually look like from a hypothetical future Earth? First, the scale is crucial to understand. Galaxies are mostly empty space. The average distance between stars is so vast that direct stellar collisions are extraordinarily unlikely. The real drama is gravitational. As the galaxies draw near, their mutual pull will warp and distort their beautiful spiral arms into long, streaming tails of stars and gas torn out by tidal forces. From within, the night sky would transform over millions of years. The approaching Andromeda Galaxy, which today is a faint smudge in the constellation bearing its name, would swell to dominate the heavens, filling half the sky with its brilliant, chaotic structure. Stars from both galaxies would be flung into new, chaotic orbits, a grand reshuffling of celestial destinies. The two galactic cores, each harboring a supermassive black hole, will begin their own intricate orbit around each other, eventually spiraling inward over hundreds of millions of years. As they do, they will stir up and heat the surrounding gas, triggering brilliant bursts of new star formation. The sky would blaze with the light of newborn star clusters, even as the familiar structure of the Milky Way's band is utterly erased. After several close passes over 1 to 2 billion years, the galaxies will finally lose their individual identities and coalesce into a single, massive, and largely featureless galaxy, an elliptical blob of stars. Astronomers have already given this future hybrid a name, Milkdromeda. Our Sun, if it still exists, will likely be flung into a much wider orbit within this new galactic empire. This event is a slow-motion destiny written in the stars, a reminder that even the grandest structures we see as permanent are merely temporary arrangements in an ever-evolving universe. That slow-motion galactic collision is a future of chaotic splendor, but there exists in the present universe a place of almost unimaginable emptiness, a void so vast it feels less like a region of space and more like a cosmic error. This is the Boötes void, and its discovery in 1981 sent a shockwave through cosmology. While surveying the distribution of galaxies, astronomer Robert Kirshner and his colleagues stumbled upon a spherical hole in the cosmic tapestry, a region in the constellation Boötes roughly 330 million light-years wide that contained almost nothing. To grasp that scale, if you placed our Milky Way at the very center of this void, you would see nothing but blackness in every direction. The first galaxy beyond our own would be so distant that its light, traveling since the dawn of the dinosaurs, would only have reached us in the 1960s. In a universe we believe is built on a web-like structure of filaments and clusters, this great nothingness is a profound anomaly. It is not completely empty. Surveys have found about 60 galaxies scattered within its immense volume, but in a region of that size, you would normally expect to find at least 2,000. It is a cosmic desert of staggering proportions, where the average distance between galactic oases is a lonely 100 million light-years. Its existence challenges our best models of how the large-scale structure of the universe formed after the Big Bang. The prevailing theory of cosmic evolution says that tiny quantum fluctuations in the early universe were amplified by gravity, with matter slowly clumping together, leaving behind interconnected bubble-like voids. But the Boötes void is far larger than any bubble our simulations typically produce. How could such a tremendous nothing come to be? One leading theory is that it is not a single void, but the result of several smaller voids merging together over billions of years, like soap bubbles coalescing into one gigantic cavity. Another, more speculative idea ties it to the phantom force of dark energy, suggesting that in this particular region, dark energy might have acted more strongly or earlier, pushing matter apart with exceptional efficiency and preventing galaxies from ever forming. There is also the haunting possibility that we are simply misreading the geometry, and the void is not a perfect sphere but an elongated, tunnel-like structure that we happen to be looking down the barrel of, making it appear emptier than it truly is. Regardless of the explanation, the Boötes void stands as a monument to scale and absence. It forces us to confront the fact that the universe is not uniformly filled with splendor, that within the grand cosmic web there exist realms of profound and terrifying solitude, places where the darkness between the stars is not just an interval but the entire story. The profound solitude of the Boötes void is a cosmic desert, but our own planet is constantly being bombarded by messengers from the most violent places in the universe. These are not spaceships but subatomic bullets, particles from deep space slamming into Earth's atmosphere with energies that defy belief. We call them ultra-high energy cosmic rays, and they carry more punch in a single, invisible speck than a major league fastball. To put it in perspective, the most powerful particle accelerator ever built by humans, the Large Hadron Collider, can smash protons together with an energy of about 13 trillion electron volts. The most extreme cosmic rays we have detected hit our atmosphere with energies exceeding 100 quintillion electron volts, millions of times more powerful. They are the universe's natural particle accelerators, operating on a scale we cannot hope to replicate. Catching these fleeting phantoms requires an observatory of continental size. The premier facility is the Pierre Auger Observatory in Argentina, a sprawling network of over 1,600 water tanks spread across 3,000 square kilometers of prairie, an area larger than Rhode Island. When an ultra-high energy cosmic ray strikes the atmosphere, it creates a cascading shower of billions of secondary particles. These particles spread out, traveling at nearly the speed of light, and when they hit the water in the tanks, they produce a faint flash of blue light called Cherenkov radiation. By timing when the wave of particles hits different tanks, scientists can trace the shower back to the direction of the original cosmic ray in the sky. But here lies the central puzzle, a theoretical barrier known as the Greisen-Zatsepin-Kuzmin, or GZK cutoff. Space is not a perfect vacuum. it is filled with the faint, cold glow of the cosmic microwave background radiation, the afterglow of the Big Bang. For a proton traveling across intergalactic space at these insane energies, that ancient light is not a gentle glow, it is a wall of high-energy photons. A collision between the ultra-high energy proton and a CMB photon should be catastrophic, sapping the proton's energy over a relatively short cosmic distance of about 150 million light-years. According to this physics, we should not see any cosmic rays with energies above the GZK cutoff arriving from sources beyond our local galactic neighborhood. Yet we do. This means these unimaginably powerful particles must originate from somewhere relatively nearby in cosmic terms, within our own galactic backyard or the closest galaxies. But from what? The source must be an engine of almost incomprehensible power, capable of accelerating a single proton to such a velocity. The leading suspects are the most energetic objects we know, active galactic nuclei, where material spiraling into a supermassive black hole releases jets of plasma moving at nearly light speed. Gamma-ray bursts, the most luminous explosions in the universe since the Big Bang, are another prime candidate. Some theories even point to the violent mergers of neutron stars or the eruptions from magnetars. Yet, when astronomers point their telescopes toward the arrival directions of these cosmic bullets, they often find nothing obvious, no brilliant quasar or recent burst at the right spot. It is as if we are being shot at by a cosmic sniper who leaves no muzzle flash. The mystery deepens because these particles are electrically charged, so their paths are bent and scrambled by the magnetic fields that permeate interstellar and intergalactic space. By the time they reach us, they are not pointing directly back to their source, but give only a vague hint of their origin. The existence of these particles is a double enigma. They defy the expected energy loss from simply traveling through space, and they hide their birthplace from our most powerful telescopes. They are the ultimate cosmic fingerprints left at the scene of a crime, but with no suspect in sight. Those cosmic bullets of unimaginable energy are fired from hidden accelerators, but the universe also forges treasures of almost mythic beauty in the crucibles of alien suns. Orbiting a star 41 light-years away in the constellation Cancer is a world that seems ripped from the pages of science fiction, a super-Earth called 55 Cancri. This planet is a staggering 8 times more massive than our own and twice as wide. But its true marvel lies not in its size, but in its probable composition. Based on meticulous analysis of the light from its host star, astronomers have found it to be extraordinarily rich in carbon. This, combined with the planet's immense density, paints a startling picture. The crushing pressures deep within this world could have crystallized its carbon into a vast planetary-scale lattice of diamond. We may be looking at a glittering jewel of a planet, a cosmic diamond larger than our entire world. The conditions on this gemstone world are as extreme as its composition. 55 Cancri orbits so close to its star that a full year there lasts a mere 18 hours. This proximity locks the planet in a gravitational embrace known as tidal locking, meaning one hemisphere permanently faces the blistering heat of its sun, while the other is cast into eternal night. The dayside is a searing hellscape with surface temperatures soaring above 2,400 degrees Celsius, hot enough to melt iron and vaporize rock. Scientists believe this side is likely a global ocean of molten lava, a shimmering, incandescent sea under a black, star-filled sky. The night side, while cooler, is still unimaginably hot by earthly standards. The immense internal heat from the planet's radioactive core and the scorching winds that might circulate from the dayside could keep even the dark hemisphere glowing. How does a diamond planet even form? The story begins with its star. 55 Cancri is a binary system, and the primary star has a much higher carbon-to-oxygen ratio than our Sun. This means the primordial disk of material from which its planets coalesced was rich in carbon compounds like graphite and carbides. In the right pressure cooker environment, which the interior of a massive, rocky planet provides, that carbon can be compressed into the crystalline structure of diamond. It is a natural geological process just taken to a cosmic extreme. This world is not a solid sphere of flawless gemstone, of course. Its structure would be a complex, layered world, perhaps with a diamond-rich mantle beneath a thin, volatile atmosphere of vaporized rock and carbon compounds. The very thought challenges our imagination, a landscape where mountains might be literal crystal and rivers could flow with molten silicon. The existence of 55 Cancri E is a glittering testament to the bizarre and wonderful diversity of worlds that fill our galaxy. It shatters our solar system-centric view of what a planet can be. We grew up learning about rocky worlds like Earth and Mars and gas giants like Jupiter and Saturn. But the cosmos has laboratories for chemistry and physics we can scarcely dream of, forging planets of diamond, worlds of solid iron, or globes shrouded in burning ice. Each discovery like this rewrites the catalogue of possibility, reminding us that the universe is not only stranger than we imagine, but often more brilliant. That diamond world gleams with the cold beauty of alien chemistry, but from the heart of our own galaxy erupts a violence of an entirely different magnitude. Towering above and below the Milky Way's serene spiral disk are two colossal, ghostly structures, each a seething bubble of high-energy particles stretching 25,000 light-years into the emptiness. If our eyes could see in gamma rays, the highest energy form of light, the night sky would be dominated by this hourglass-shaped monument, a pair of titanic geysers blasting from the galactic core. We call them the Fermi bubbles, named for the telescope that discovered them. For years, the diffuse gamma-ray glow of our galaxy was considered a uniform background noise, a cosmic static. But in 2010, scientists processing data from the Fermi Gamma-Ray Space Telescope made a startling subtraction. They carefully mapped and then removed all the known sources of gamma rays, the pulsars, the supernova remnants, the distant active galaxies. What remained was not random noise, but a stark, distinct shape. Two enormous, symmetrical lobes of intense gamma-ray emission, one to the north and one to the south of the galactic center, with sharp, well-defined edges. They looked like nothing so much as the aftermath of a colossal explosion, a pair of cosmic lungs inflated by a single, unimaginable breath from the galaxy's core. Their size is almost incomprehensible. From tip to tip, they span 50,000 light-years, half the diameter of the Milky Way itself. We are living inside the lower reaches of this immense structure, with one bubble towering above our galactic plane and the other extending far below it. So what cosmic force could possibly inflate such gargantuan balloons? All evidence points to the sleeping giant at the very center of our galaxy, the supermassive black hole known as Sagittarius, a star. Today, this black hole is relatively quiet, a dormant beast feeding on only a trickle of gas. But the Fermi bubbles are a fossil record, proof of a cataclysmic temper tantrum in our galaxy's past. The leading theory is that several million years ago, Sagittarius, a star, awoke in a spectacular fashion. A massive cloud of gas, perhaps a whole star cluster, ventured too close and was torn apart by the black hole's immense gravity. As this colossal meal spiraled inward, it formed a searing, bright accretion disk, and the black hole did not consume it quietly. Instead, it channeled a fraction of that infalling material into two opposing relativistic jets, beams of plasma shooting out at nearly the speed of light from its poles. These jets, punching through the surrounding gas of the galactic center, would have acted like cosmic blowtorches, inflating the giant bubbles we see today. The sharp edges of the bubbles suggest this was not a slow, steady wind, but a rapid, powerful outburst that lasted perhaps 100,000 to 1 million years, a brief event on galactic timescales. Within these bubbles, the gas is not calm. It is a superheated plasma, a soup of charged particles and magnetic fields, with temperatures in the millions of degrees. The gamma rays we detect are produced as high-speed electrons, accelerated by the blast, slam into the slower-moving photons of starlight and the cosmic microwave background, boosting them into the gamma-ray regime in a process called inverse Compton scattering. The Fermi bubbles are therefore a time capsule, a lingering echo of a moment when our galaxy's heart roared. They tell us that even quiet, spiral galaxies like our own have a violent history, that the serene pinwheel of stars we see is just the present face of a system that has experienced episodes of unimaginable fury. They are a permanent reminder that we orbit not just a star, but a galactic center with the power to reshape its entire neighborhood in a single, monumental blast. That galactic explosion left a permanent scar, but sometimes the violence at a galaxy's heart can launch its very core into the void. Drifting through the darkness between galaxies is a monster on the move, a supermassive black hole with the mass of 20 million suns, fleeing the scene of a cosmic crime and leaving a brilliant clue behind it. The Hubble Space Telescope captured this astonishing scene, a thin, almost straight line of young, blue stars stretching an incredible 200,000 light-years across space. At the tip of this stellar contrail, like a locomotive at the head of a train, speeds the black hole itself. This is no ordinary rogue star. It is the central engine of an entire galaxy, violently evicted from its home. The image is surreal, a cosmic brushstroke of newborn suns painting a path through the intergalactic emptiness. How does a black hole, an object with gravity so strong not even light can escape, become a runaway? The answer lies in the chaotic dance that follows a galactic merger. When two galaxies collide, their central supermassive black holes eventually sink to the new common center, forming a binary pair. If a third galaxy joins the fray, bringing its own black hole, the resulting three-body gravitational interaction can become wildly unstable. In this celestial game of billiards, one of the black holes can be flung outward at tremendous speed, a gravitational slingshot effect on a scale almost beyond comprehension. In this case, astronomers believe that is precisely what happened. The runaway black hole is moving so fast it could travel the distance from Earth to the Moon in just 14 minutes. As it plows through the thin gas that permeates intergalactic space, the shock of its passage compresses and heats the material. This gas, now under incredible pressure, cools and collapses behind the speeding behemoth, igniting into a long, narrow trail of new stars. It is a unique form of cosmic creation, a stellar nursery born not in the quiet cradle of a nebula, but in the supersonic wake of a gravitational titan. This discovery shatters the quiet assumption that supermassive black holes are forever anchored to the center of their galaxies. It proves they can be ejected, becoming intergalactic wanderers. This has profound implications for our understanding of how galaxies evolve, and how many such lone black holes might be silently drifting through the dark, invisible except for the rare and spectacular birth of stars they leave behind. It is a stunning demonstration that even the universe's most powerful anchors can be torn loose by forces greater than themselves. That runaway black hole carves a path of newborn stars through the void, but within our own solar system, a different kind of geometric perfection has been etched into the clouds of a giant. At Saturn's North Pole, a hexagon wider than our entire planet has persisted for decades, a six-sided jet stream of astonishing precision encircling a perpetual storm. This is not an artist's concept or a trick of the light. It is a real, stable feature in the turbulent atmosphere of a gas giant, first glimpsed by the Voyager probes in the 1980s and later studied in breathtaking detail by the Cassini spacecraft. Imagine a hurricane, but one with six sharply defined walls, each side stretching over 13,000 kilometers, large enough to swallow two Earths side by side. The structure rotates with the planet's deep interior, completing one revolution roughly every 10 hours and 39 minutes, and it acts as a barrier, containing weather systems within its boundaries and creating a unique, swirling cap of clouds. For years, its very existence defied simple explanation. How could such a rigid geometric form arise naturally in a fluid, chaotic environment like a planetary atmosphere? The answer appears to lie not in alien architecture, but in the elegant physics of rotating fluids. Through laboratory experiments and sophisticated computer simulations, scientists have recreated similar polygonal shapes by spinning fluids at different speeds. The key is the difference in wind speeds between various atmospheric jets at Saturn's high latitudes. As these bands of gas shear past one another, they can generate a standing wave pattern, a stable, oscillating disturbance that pins itself in place. On a rapidly rotating sphere, under the right conditions, that standing wave can take the form of a polygon, with a hexagon being a particularly stable configuration. It is akin to the way a vibrating guitar string creates a standing wave with fixed nodes, or how you can stir a cup of coffee to create a small, stable dimple in the center. The hexagon is in essence a giant planetary-scale version of this phenomenon, a natural stability carved by wind and spin, yet understanding its mechanism does not strip away its wonder. The sheer longevity of the hexagon is what continues to mesmerize. It has endured across multiple Saturnian seasons for at least 40 Earth years and likely much longer, maintaining its razor-sharp edges against the relentless forces of atmospheric turbulence. Its geometric perfection, set against the soft, banded beauty of Saturn's clouds, serves as a humbling reminder. The universe often writes its most stunning art not in stone, but in wind and time, proving that nature's rulebook holds chapters on order we are only beginning to read. Saturn's geometric perfection is carved by wind, but far beyond its orbit, in the frozen dark where the sun is just a bright star, a different kind of order hints at a hidden architect. The strange, clustered orbits of several distant icy bodies are pointing, like cosmic arrows, toward the possible existence of a giant world we have never seen. This is the compelling mystery of Planet 9. The story begins not with a telescope image, but with a pattern noticed in the data. Astronomers Mike Brown and Konstantin Batygin were studying the distant Kuiper belt, the realm of Pluto and its icy cousins, when they realized something was off. A handful of the most far-flung objects, those with orbits taking thousands of years, shared a peculiar trait. Their elongated paths were not randomly oriented in space. Instead, their points of closest approach to the Sun, their perihelia, were clustered together in the same general region of the solar system. Even more strangely, their orbits were all tilted in a similar direction. For this to happen by pure chance is astronomically unlikely, like finding several scattered compass needles all pointing northeast. The simplest and most thrilling explanation is gravity. A massive, distant planet with an orbit far beyond Neptune could be shepherding these smaller objects into this strange alignment. Its gravitational pull, exerted over billions of years, would act like an invisible hand organizing the chaos. Based on the precise way these distant objects are grouped, Batygin and Brown calculated the probable nature of this ghostly shepherd. Planet 9, if it exists, is no lightweight. It is likely a super-Earth or a mini-Neptune with a mass 5 to 10 times that of our own world. Its orbit would be a colossal, stretched ellipse, taking an astonishing 10,000 to 20,000 years to complete a single journey around the Sun. At its most distant, it could be over 20 times farther from the Sun than Neptune, a lonely sentinel in the profound cold. The hunt for this world is a monumental challenge. Its incredible distance means it reflects virtually no sunlight, making it incredibly faint. Its slow, ponderous orbit means it will not move noticeably against the starry background in a single night or even over several years. Astronomers are not looking for a moving dot, they are looking for a nearly stationary speck of light in a sky filled with billions of stars. This requires painstakingly comparing images of the same patch of sky taken months or years apart, searching for one faint point that has shifted just a tiny amount. It is a needle in a haystack the size of the cosmos. Yet, the search is underway using some of the world's most powerful telescopes, like Subaru in Hawaii, to scan the most likely regions of sky predicted by the orbital clues. Finding Planet 9 would be more than just adding a new world to our solar system map. It would rewrite the story of our cosmic neighborhood's formation, explaining how such a large world ended up so far out, and it would solve the lingering mystery of the Kuiper Belt's abrupt edge. For now, it remains a gravitational ghost, a prediction written in the paths of tiny, distant worlds, waiting for the moment when our gaze finally finds the hand that guides them. This search for a hidden giant is a local mystery, but the grandest structure of all surrounds us on a scale so vast it redefines the word immense. Our universe is not a random scatter of galaxies like stars tossed across black velvet. Instead, it is a precisely woven tapestry, a cosmic web of breathtaking complexity. This is the large-scale structure of everything, and it reveals a universe built not on chaos, but on an architecture of filaments and void. If you could pull back far enough to see billions of light years at a glance, you would witness galaxies not as isolated islands, but as glittering nodes along vast, interconnected threads of dark matter and gas. These threads stretch across the emptiness, connecting in dense knots where great clusters of galaxies reside, and between them lie the immense, echoing deserts of nothingness, the cosmic voids. The Boötes void we discussed earlier is just one of many such empty chambers in this grand celestial cathedral. How did this intricate web come to be? The story begins in the first fleeting moments after the Big Bang in a seething sea of energy. At this quantum scale, tiny fluctuations were inevitable, minute differences in density from one point to the next. These were not flaws, but the seeds of all future structure. Then, in a fraction of a second, the universe underwent a period of hyper-expansion called inflation, stretching these quantum ripples to cosmic proportions. Imagine blowing up a balloon with a faint, microscopic pattern drawn on it. As the balloon inflates to the size of a planet, that pattern becomes a continent-spanning landscape. After inflation, gravity took over as the great sculptor. Over hundreds of millions of years, gravity began to pull matter toward those slightly denser regions. Dark matter, which interacts only through gravity, led the way, collapsing first into an invisible scaffold. Ordinary matter, the gas that would become stars and galaxies, then flowed along these dark matter highways, condensing at the intersections and nodes. The result is a universe that looks, in our most advanced computer simulations, exactly like a neural network or a froth of soap bubbles. A three-dimensional web of matter with vast empty spaces in between. We are not just theorizing this web, we have mapped it. Massive galaxy surveys like the Sloan Digital Sky Survey have painstakingly measured the positions and distances of millions of galaxies. When those points are plotted in 3 dimensions, the pattern emerges from the data, a cosmic fingerprint. Galaxies align along delicate filaments, and we can even trace the slow, river-like flow of galaxies along these threads toward the massive clusters, just as we are flowing toward the great attractor within our own local filament, Laniakea. This is the universe's true skeleton, built from the ghostly bones of dark matter and illuminated by the shining cities of galaxies that light its nodes. It is a structure that confirms our deepest theories of cosmic evolution, a pattern written in the sky that tells us the entire history of the cosmos, from quantum whisper to galactic web, is one continuous, elegant story. That cosmic web of galaxies is a tapestry of chaos and connection, but sometimes the universe creates a single, perfect circle that seems to defy the very idea of disorder. Floating in the constellation Serpens, 600 million light-years away, is a galaxy so geometrically flawless it looks like a cosmic bullseye or a piece of celestial jewelry. This is Hoag's object, a galaxy unlike any other in our catalogues. At its heart lies a dense, spherical core of ancient yellowish stars, glowing with the warm light of stellar old age. Surrounding this core is a breathtaking, perfectly circular ring of brilliant blue stars, young, hot, and luminous. Between the two is a gap of profound darkness, a wide, empty channel that cleanly separates the ring from the core. There are no spiral arms, no connecting bridges of stars or dust, just a perfect circle of stellar birth around a serene, golden center. Its beauty is so striking and symmetric that when astronomer Arthur Hogue discovered it in 1950, he initially thought it might be an optical illusion, a trick of gravitational lensing. But it was real, a galaxy that had somehow organized itself into a form of stunning, minimalist perfection. The mystery of Hogue's object is not just its beauty, but its origin. How does a galaxy become such a perfect ring? The most widely accepted theory points to a cataclysmic event billions of years in its past, a galactic collision. The idea is that a smaller galaxy, a cosmic intruder, once plunged directly through the heart of what was then a more typical spiral or disk galaxy. The gravitational shockwave from this bullseye impact would have sent ripples through the victim galaxy's gas, much like a stone dropped in a pond. These ripples, known as density waves, would have compressed the gas in a perfect, expanding circle, triggering a colossal burst of star formation at that specific radius. Over time, the stars already in the central region would have settled back into a tight core, while the brilliant new stars born from the compressed gas would continue to shine in the expanding ring. The intruder galaxy itself, having delivered its disruptive blow, would have sailed on into the void, leaving behind this exquisite, circular scar of new starlight as its only calling card. The haunting part of this theory is the emptiness where the culprit should be. In the vast space around Hogue's object, astronomers have found no obvious remnant, no distorted galaxy that could be the perpetrator. It has vanished completely, leaving behind only this perfect, silent witness to a violence that has long since faded. Other, rarer theories suggest it could be the result of an extreme form of bar instability, where a central bar of stars forms and then dissolves, flinging material outward into a ring, but the pristine symmetry of Hogue's object makes this less likely. This galaxy stands as a cosmic paradox, a symbol of serene order born from unimaginable chaos. It reminds us that the universe often writes its most beautiful poems with the grammar of catastrophe, and that what we see as a perfect, timeless circle is often just a single, frozen frame in a long and violent story. That perfect cosmic ring is a testament to the universe's capacity for order, but at the very foundation of reality lies a deeper and more personal mystery, one that asks why we are here at all. The universe should be empty. According to our best theories of physics, the Big Bang should have created equal amounts of matter and its perfect opposite, antimatter. For every proton born, an antiproton should have emerged. For every electron, a positron. Matter and antimatter are cosmic twins, identical in mass but opposite in charge and other quantum properties. When they meet, they annihilate each other in a flash of pure energy, leaving nothing behind. If the cosmos began with perfect symmetry, every particle of matter should have found its antimatter twin, and the entire universe should have vanished in a brilliant, all-consuming flash of light, leaving behind an eternal, featureless sea of radiation. Yet here we are, in a universe filled with stars, planets, and life, all made of matter. The antimatter has almost entirely vanished. This is not just a puzzle, it is the central question of our existence. Why does anything exist? The answer must be that the symmetry was broken, that for every billion pairs of matter and antimatter particles that annihilated in the early universe, a single particle of matter was left over. That 1 in a billion survivor is everything we see. The entire observable universe, every galaxy, every atom in your body, is the leftover ash from that near-total annihilation. So what tipped the scales? Physicists call the necessary imbalance CP violation. The C stands for charge conjugation, which means swapping a particle for its antiparticle. The P stands for parity, which is like looking at the universe in a mirror. For a long time, it was assumed the laws of physics were perfectly symmetric under both operations, that a universe of antimatter would behave exactly like our own, and that a mirror universe would be indistinguishable. But in 1964, an experiment studying the decay of particles called kaons found a tiny, shocking crack in that mirror. The decay rates of kaons and antikaons were not perfectly identical. There was a slight preference, a minuscule bias in the laws of physics themselves that favored matter over antimatter. It was as if the universe had a built-in, fundamental preference for one hand over the other. This discovery of CP violation was monumental, proving the symmetry could be broken, but the amount observed in kaon decays is far too small to account for the overwhelming dominance of matter we see today. It is a clue, but not the full answer. The hunt for the source of this cosmic bias is one of the most urgent quests in modern physics. Today, scientists are chasing this ghost of imbalance in colossal underground laboratories and particle colliders. At the Large Hadron Collider at CERN, experiments like LHCb are dedicated to studying the behavior of beauty quarks and their antiparticles, searching for even subtler signs of CP violation. By smashing protons together at nearly the speed of light and meticulously tracking the debris, they are looking for a difference, however tiny, in how often certain particles decay compared to their antimatter counterparts. Other experiments study neutrinos, the ghostly particles that barely interact with matter, to see if they might hold the key. Each measurement is a search for the fingerprint of the process that saved the universe from self-destruction. The quest is to find a source of CP violation powerful enough to explain our 1 in a billion survival. Some theories point to conditions in the very first moments after the Big Bang, during a period of hyper-expansion called inflation, where quantum fields could have tilted the balance. Others suggest the answer lies with neutrinos or with particles we have not yet discovered. Solving the antimatter mystery is more than an academic exercise. It is the search for the original cause of everything we know. It asks why the laws of physics contain a faint bias for existence, a whisper of preference that allowed structure, complexity, and ultimately, us, to emerge from a fireball that should have left only silence. That faint bias for existence allowed the universe to survive, but the cosmos also forges engines of pure magnetic terror. Among the stellar zombies left behind by supernova, none are more violently unstable than the magnetar. Imagine the core of a giant star, larger than our sun, collapsing in on itself. If conditions are just right, this catastrophic birth does not simply create a dense neutron star, it supercharges it. The collapsing magnetic field of the progenitor star becomes concentrated, amplified to almost unimaginable levels, transforming the newborn remnant into a cosmic powerhouse with a magnetic field 1,000 trillion times stronger than Earth. If a magnetar were located halfway between Earth and the Moon, its magnetic field would effortlessly strip the information from every credit card on the planet. This is not just a strong magnet, it is a fundamental force of nature made manifest in a city-sized object. The life of a magnetar is one of constant, pent-up tension. Its crust, a rigid lattice of iron nuclei 10 billion times stronger than steel, is under unimaginable strain from the twisting, titanic magnetic fields trapped beneath. This creates a ticking time bomb. Eventually, the crust cannot take the stress. It cracks. A starquake on a magnetar is nothing like an earthquake. It is a global shattering event that releases more energy in 1/10 of a second than our sun will emit in 100,000 years. This energy erupts not as sound or shaking, but as a blinding flash of the highest energy radiation in the universe, gamma rays and X-rays. We call these eruptions soft gamma repeaters, a deceptively gentle name for the most violent electromagnetic explosions known. One event in particular demonstrated their terrifying reach. On December 27, 2004, a magnetar named SGR 180620, located 50,000 light-years away in the constellation Sagittarius, unleashed a giant flare. For 0.2 of a second, it became the brightest object ever detected outside our solar system, outshining the full moon in gamma rays. The wave of X-rays and gamma rays raced across the galaxy and struck Earth's upper atmosphere. In an instant, it ionized the atoms in our ionosphere, causing a sudden and profound disruption in long-range radio communications. It physically compressed our planet's magnetic field, and satellites orbiting Earth were momentarily blinded by the flash. All of this from an object so distant its light had been traveling for 50 millennia, a flash from the dawn of human prehistory that arrived just in time to remind us of the raw, untamed power lurking in the galactic dark. These magnetic monsters are the universe's ultimate proof that sometimes the most dangerous things are not the largest, but the ones under the most immense and invisible pressure. The magnetic fury of a magnetar warps space itself, but gravity can bend light into shapes of serene, circular perfection. This is the phenomenon of gravitational lensing, a direct prediction of Einstein's theory of general relativity. Einstein proposed that mass does not just create a force, it actually warps the fabric of space and time around it. Picture a heavy bowling ball placed on a stretched rubber sheet. It creates a deep depression. Now roll a marble past the bowling ball. Its path will curve, not because of a direct pull, but because it is following the curved surface. Light does the same thing. When light from a distant galaxy travels across the universe and passes near a massive object like a galaxy cluster, it does not travel in a straight line. It follows the curve in space-time created by that cluster's immense gravity. The cluster acts as a cosmic lens, distorting and magnifying the light from the object behind it. The results can be spectacularly strange. We might see multiple smeared or stretched images of the same distant galaxy, arranged around the lensing cluster like pieces of a broken mirror. Sometimes, if the alignment between the distant object, the massive lens, and our telescope is absolutely perfect, the light is bent into a complete circle. This is an Einstein ring, a halo of warped starlight, one of the most beautiful and precise confirmations of Einstein's genius in the entire sky. It is nature's own telescope, and it gives us superpowers. Because the lens magnifies the distant light, we can see galaxies that are otherwise far too faint and small for our telescopes to detect. Astronomers use these natural cosmic lenses to peer back to the very edge of the observable universe, studying the first galaxies that flickered to life after the Big Bang. But the lens does more than just magnify, it reveals the invisible. The amount of bending depends on the total mass of the foreground cluster. By meticulously measuring the distortions in the Einstein rings and the stretched arcs of background galaxies, scientists can make a precise map of the cluster's gravity. And what they find is that the visible stars and gas account for only a tiny fraction of the mass required to create such severe warping. The rest is the ghostly halo of dark matter, its distribution now charted in exquisite detail by the very light it bends. Every perfect ring and every distorted arc is therefore a double discovery, a window to the cosmic dawn and a map of the universe's hidden skeleton. Gravitational lenses reveal the hidden architecture of the cosmos, but sometimes the universe's most resilient worlds are found orbiting its most terrifying corpses. The first planets ever discovered beyond our solar system were not found around a sun like our own. They circle a pulsar, the rapidly spinning, intensely magnetic corpse of a star that died in a supernova explosion. This system, PSRB 1257+12, presented astronomers with a profound paradox in 1992. A pulsar is a neutron star, an object so dense a teaspoon of its material would weigh as much as a mountain. It emits deadly beams of X-rays and gamma rays as it spins, sweeping the sky like a cosmic lighthouse hundreds of times per second. The supernova that created this pulsar should have been an apocalypse, a blast wave of unimaginable power capable of vaporizing any pre-existing planets in the system. Yet there they were, at least 3 small worlds detected by the precise clockwork variations they caused in the pulsar's spin. How could planets survive such stellar Armageddon? The leading theory is that they did not survive, they were born from it. These are likely second-generation planets formed from the ashes of destruction. After the supernova, a disk of metallic debris, rich in heavy elements like iron and silicon, may have coalesced around the pulsar. This material could have been stripped from a companion star by the pulsar's gravity, or it could be the fallback of material from the supernova itself that did not quite escape. From this disk of stellar ashes, a new family of worlds condensed, forged in the aftermath of cosmic death. These pulsar planets are unimaginably hostile. Bathed in constant, sterilizing radiation and subject to intense gravitational tides, they are likely barren, metallic worlds, perhaps with surfaces of solid iron or crystallized carbon. Their very existence is a testament to nature's relentless drive to build order from chaos, proving that even in the aftermath of a star's violent end, the conditions for new worlds can emerge. While pulsar planets are forged in stellar fire, the hidden interiors of our own solar system's ice giants harbor a precipitation of astonishing beauty and violence. Deep within Uranus and Neptune, the familiar rules of chemistry break down under pressures millions of times greater than Earth's atmosphere. These planets are not gas giants like Jupiter, but ice giants with thick mantles of slushy, superheated water, ammonia, and methane ices. Within this strange fluid, something extraordinary is hypothesized to occur. The intense pressure and heat are thought to break apart methane molecules, liberating carbon atoms. Under these conditions, carbon is squeezed into the crystalline structure of diamond. Scientists believe these diamonds would not float but sink, as they are denser than the surrounding icy slush. The result is a slow, endless rain of diamond hailstones falling through thousands of miles of planetary interior toward the core. This is not science fiction, but a robust prediction based on laboratory experiments where researchers have used powerful lasers to recreate the extreme conditions inside these worlds, observing the formation of tiny diamond specks from hydrocarbon compounds. Imagine the scene in the perpetual darkness of Neptune's mantle, glittering stones of diamond, perhaps as large as icebergs, descending through a strange ocean of ionized water and dissolved rock. This diamond rain may have profound effects on the planet itself. As the diamonds sink, they release gravitational energy, generating heat that could help drive the planet's fierce winds and its mysteriously hot interior, which radiates more heat than it receives from the distant sun. Two different mysteries, one of survival in a radioactive graveyard, the other of gemstone precipitation in a planetary deep, both speak to the universe's endless capacity for the bizarre. They show that the physics of alien worlds operates on a spectrum of extremes, from the nuclear furnaces of dead stars to the crushing, alchemical depths of ice giants. That profound silence we listen for is not passive, but a challenge we have actively sought to break for over 6 decades. Since 1959, when astronomers first pointed a radio telescope at the stars with the intent to eavesdrop, the search for extraterrestrial intelligence, or SETI, has been a grand, patient experiment. Its premise is simple: if a civilization out there is broadcasting, we might hear it. The tools have grown from single dishes to vast arrays, scanning millions of radio channels simultaneously, and the search has expanded to look for laser pulses, megastructures, and even techno-signatures in atmospheric chemistry. Yet, after all this listening, the result remains the same: a deafening quiet. This is the great silence, and it is far more than just an empty result. It is a growing philosophical puzzle that forces us to question our most basic assumptions. The technical challenges are immense, space is vast, and we have only sampled a tiny fraction of the radio spectrum for a minuscule amount of time in a galactic ocean of billions of stars. It is like trying to hear a single, specific conversation on Earth by listening to 1 cup of seawater for 1 minute. A signal could be too faint, on a frequency we are not monitoring, or broadcast in a direction we are not looking at the precise moment we glance away. It could even be in a form of communication we have not yet conceived, using physics beyond our understanding. But as our technology improves and our search grows more sophisticated, the silence becomes louder, more pointed. It suggests that if civilizations are common, they are either not broadcasting in ways we can detect, or they are deliberately quiet. This leads us to one of the most elegant and unsettling resolutions to the Fermi paradox, the zoo hypothesis. Imagine a vast interstellar wildlife preserve. The hypothesis suggests that advanced civilizations are not only aware of our existence, but have placed us in a kind of cosmic quarantine. They observe us from a distance, adhering to a strict policy of non-interference, much like anthropologists studying an uncontacted tribe in the Amazon, or visitors to a zoo who look but do not touch. The reasoning could be ethical, to allow a young species like ours to develop naturally, free from the cultural shock or technological domination that contact might bring. It could be practical, avoiding the risks of a potentially volatile adolescent civilization. Or it could be scientific, preserving a unique sample of biological and social evolution for study. In this view, the great silence is not an absence, but a deliberate curtain drawn around our planet. The night sky is not empty, but watched. This transforms the paradox from a question of engineering, where are there ships and signals, into one of cosmic anthropology. What are the rules of engagement in a populated galaxy? Is there a universal protocol that mature civilizations follow, a prime directive written not in law, but in the hard-learned lessons of galactic history? The zoo hypothesis offers a strange comfort and a profound unease. It solves the problem of the silence, but it places us in a position we have never experienced before, not as explorers but as the observed. It suggests that our first contact may not come when we are ready, but when they decide we are. The silence of a cosmic zoo suggests a universe of careful observers, but the night sky above us holds direct evidence of a far more brutal reality. Our own Milky Way is not a peaceful island, it is a predator. The serene band of light we see is a galactic graveyard, built from the corpses of smaller galaxies it has consumed over billions of years. This is galactic cannibalism, and it is how all large galaxies grow. The process is not a sudden, catastrophic collision, but a slow, gravitational dismemberment. A smaller satellite galaxy, drawn in by the immense pull of the Milky Way's dark matter halo, begins a long, decaying orbit. With each pass, the larger galaxy's tidal forces, the difference in gravity between the near and far sides of the smaller galaxy, act like a cosmic hand pulling it apart. Stars are stripped from its outer layers, first in delicate streams, then in great plumes, until the satellite's core is finally dissolved and digested into the galactic halo. We are witnessing this very process today. The victim is the Sagittarius dwarf elliptical galaxy, a tiny companion discovered only in 1994 because it was hidden behind the dense star fields of our own galactic center. It is now in its death throes. Over its multiple orbits, the Milky Way has stretched it into a spectacular stellar river that wraps around our entire galaxy like a great loop of tinsel. This is a tidal stream, a ribbon of orphaned stars tracing the ghostly path of their devoured parent. These streams are more than just celestial debris, they are forensic evidence. By mapping the precise positions and motions of stars within a tidal stream, astronomers can rewind the cosmic clock. They can trace the stream's path backward, reconstructing the orbit of the devoured galaxy, determining how many times it circled the Milky Way, and even estimating when it first fell into our gravitational grasp. The Sagittarius stream tells a story of a satellite that has been orbiting and being stripped apart for perhaps 8 or 9 billion years, almost as long as the Milky Way itself has existed. But the clues go deeper. The shape and density of a tidal stream are exquisitely sensitive to the distribution of mass in the host galaxy, particularly the invisible dark matter halo. As the stream of stars orbits, it responds to the gravity of all the matter it passes through, both seen and unseen. By studying how the stream is twisted and clumped, scientists can create a detailed map of the Milky Way's dark matter, weighing its halo and revealing its shape. The streams act like cosmic plumb lines, tracing the contours of our galaxy's deepest gravitational secrets. Our sky is therefore a palimpsest, a document written over many times. The smooth disk we admire is the latest chapter, but beneath it, written in the faint, flowing script of tidal streams, is a violent history of conquest and consumption. We are not just citizens of a spiral galaxy, we are inhabitants of a galactic empire, living atop the ruins of its ancient conquests. The cannibalized stars of our galaxy's past orbit a present built from the ashes of the universe's first 3 minutes. In that searing dawn, protons and neutrons fused into the first atomic nuclei, a process called Big Bang nucleosynthesis. Our mathematical models of that event are spectacularly successful, predicting the cosmic abundances of hydrogen and helium with near-perfect accuracy. But they also predict a specific amount of a third element, lithium-7. And here, the math fails. The models say old stars, the pristine fossils of the early cosmos, should contain about 3 times more lithium than we actually measure. This is the lithium problem, a small but persistent crack in our otherwise flawless story of creation. Where did all the lithium go? One possibility is that our understanding of stellar physics is incomplete. Perhaps these ancient stars have internal processes, slow mixing currents or nuclear reactions we have not fully accounted for that gradually destroy lithium over billions of years, scrubbing it from their atmospheres. Another, more radical idea points to the physics of the Big Bang itself. Could unknown particles, like certain types of dark matter, have been present in that primordial soup, altering the nuclear reaction rates just enough to produce less lithium from the start? This tiny discrepancy is a reminder that even our most successful cosmic stories might still be missing a few crucial characters. If the lithium problem is a missing piece, the baryon asymmetry is the gaping hole at the center of existence. We touched on the antimatter mystery earlier, but baryon asymmetry is the formal, staggering name for it. Baryon refers to the family of heavy particles, primarily protons and neutrons, that make up the atoms in everything you see. The asymmetry is the fact that these particles overwhelmingly won out over their antimatter counterparts. For the universe to exist as we know it, this imbalance had to be forged in the first fractions of a second after the Big Bang. The conditions required are named the Sakharov conditions after the physicist who outlined them. First, the universe had to be out of thermal equilibrium, a state of seething, chaotic change rather than calm uniformity. This likely happened during cosmic inflation or other phase transitions. Second, there needed to be processes that violated both charge symmetry and charge parity symmetry, the CP violation we discussed, providing a tiny but crucial bias in the laws of physics themselves. Third, these processes had to violate baryon number, meaning they could actually create more baryons than antibaryons, not just separate them. While we have observed CP violation, we have never seen baryon number violation in any laboratory. Its source remains one of the great hunted ghosts of particle physics. Some theories suggest it could be linked to the decay of hypothetical particles predicted by grand unified theories, or even to interactions involving neutrinos. Solving this is not just about fixing an equation, it is about explaining why there is something rather than nothing. The lithium problem asks where a specific ingredient went, but baryon asymmetry asks why the kitchen itself was ever built. Together, they are bookends to the universe's first moments, one a subtle error in the ledger, the other the fundamental reason the ledger has any entries at all. The universe's fundamental laws may not be as fixed as we once believed. Our quest to understand dark energy and dark matter has led physicists to the edge of known science, where they are now hunting for ghosts that could rewrite the rulebook of reality itself. One of the most intriguing candidates is the chameleon particle. This is not a particle with scales, but one with a behavior that gives it its name. The chameleon particle is a hypothetical explanation for dark energy, the phantom force accelerating the universe's expansion. Its defining trick is that its mass and interaction strength are not constant. They change dramatically based on the density of its surroundings. In the near-perfect vacuum of interstellar space, where matter is sparse, the chameleon particle would be very light and have a long-range influence, pushing galaxies apart and driving cosmic acceleration. But bring it into a dense environment like a laboratory on Earth, and it would become incredibly heavy and short-ranged, effectively hiding in plain sight. This is why our most sensitive detectors on Earth have failed to find dark energy. The chameleon would be suppressed, its effects squashed to undetectable levels by the mere presence of our planet's mass. To catch it, scientists must get clever, designing experiments in regions of extremely low density. Some proposals involve sending delicate atomic interferometers into the vacuum of space, far from Earth's bulk, where the chameleon's true nature might finally reveal itself. This particle is a master of disguise, a cosmic fugitive whose properties are a direct reflection of its environment. The search for such a phantom is part of a broader, more profound revolution, the hunt for a fifth fundamental force. For centuries, we have described the universe with four forces: gravity, electromagnetism, the strong nuclear force that binds atomic nuclei, and the weak nuclear force behind radioactive decay. This quartet explains everything from the orbit of planets to the shine of stars. Yet, the stubborn mysteries of dark matter and dark energy have physicists wondering if the list is complete. Could there be a fifth force, a subtle interaction that only manifests over specific distances or with certain types of matter? Finding it would be one of the greatest discoveries in the history of science. The experiments to test this are marvels of precision, conducted in ultra-quiet laboratories shielded from cosmic rays and vibrations. One approach uses neutrons, the neutral particles in an atom's nucleus. By firing beams of neutrons at walls of different materials and measuring how many pass through, scientists can search for an unexpected scattering that could signal a new, weak force acting between the neutrons and the atoms in the wall. Another method probes the very structure of atoms themselves. By using lasers to excite electrons into higher energy orbits and measuring the transition with exquisite accuracy, researchers can check for tiny deviations from the predictions of standard quantum electrodynamics. Any discrepancy could be the fingerprint of a fifth force tweaking the internal workings of matter. These are not searches for massive objects, but for whispers in the data, for a slight tremor in the otherwise perfect rhythm of physical law. Each null result narrows the possibilities, and each anomaly, however small, sends a thrill through the scientific community. We are testing the universe at its most fundamental level, asking if the forces we grew up learning are the entire story or merely the opening chapter. Two phantom satellites haunt the edges of our orbital space, one born from myth and the other from genuine mystery. The first is the infamous Black Knight satellite, a legend that speaks of an ancient alien object silently circling our planet for 13,000 years. The story is woven from many threads, a tapestry of misinterpretation and imagination. Its supposed evidence includes anomalous radio signals reported by Nikola Tesla in 1899, strange echoes heard by amateur radio operators in the 1920s, and grainy photographs from early space missions showing unidentified debris. The most persistent image, often cited as the Black Knight itself, is a dark, angular shape photographed during a 1998 space shuttle mission. The reality, however, is far more mundane. That iconic photo almost certainly shows a thermal blanket, a piece of multilayered insulation that had come loose during a spacewalk. These blankets, designed to regulate a spacecraft's temperature, are often lost and can tumble in orbit for years, catching the light in strange ways. The earlier radio signals have plausible natural explanations, from atmospheric phenomena to terrestrial interference. The Black Knight is a classic modern myth, a cosmic ghost story built from the discarded litter of our own space age. Its mystery not in its existence, but in our enduring desire to see a visitor in our own reflection. Far more intriguing is the genuine enigma of 1991 VG. This is a real object discovered by astronomer James Scotty in November of that year. What made it instantly peculiar was its orbit, a path around the Sun that was eerily similar to Earth's own. It was small, perhaps only 10 to 30 meters across, and it occasionally made close passes by our planet. Most natural asteroids do not follow such Earth-like trajectories. They tend to have more elongated or inclined orbits. This unusual path immediately sparked questions. Could it be a piece of space junk from our own early explorations, like a spent rocket booster from an Apollo mission? The timing was plausible. Or, given its small size and peculiar orbit, could it be something else entirely, perhaps an alien probe? Scientists scrambled to analyze its light curve, the pattern of how its brightness changed as it rotated. The data suggested it was tumbling, a motion common for both natural asteroids and derelict human-made objects. To this day, its origin remains officially unclassified. The most likely explanation is that it is a natural near-Earth asteroid, perhaps one that was recently ejected from the main belt by a gravitational nudge from Jupiter. Yet the possibility that it is a relic of the early space age, a forgotten piece of our own history returning like a ghost, or something even more unexpected, ensures that 1991 VG retains its tiny, tantalizing question mark in the sky. It is a reminder that not every mystery needs to be an ancient alien artifact. Sometimes the truth is simply a piece of our own past or a natural wanderer that we have not yet been able to fully identify. Deep within the galactic core, where the supermassive black hole resides, another persistent and unexplained light refuses to be ignored. This is the galactic center excess, a diffuse, mysterious glow of gamma rays that bathes the region around Sagittarius, a star. It was discovered not by a single observation, but by a careful process of elimination using data from the Fermi Gamma Ray Space Telescope. Scientists created a detailed model of all the known gamma ray sources in that crowded region, the glowing remnants of supernova, the jets from binary star systems, the diffuse emission from cosmic ray collisions. They subtracted all of that expected light from the Fermi map. What remained was a smooth, spherical halo of excess gamma ray emission, centered on the very heart of our galaxy. It was a ghost in the data, a signal with no obvious source. The hunt for its origin quickly centered on two compelling and radically different possibilities. The first is a story of cosmic ghosts annihilating each other. If dark matter is made of weakly interacting massive particles, or WIMP, then the dense concentration of dark matter predicted to exist at the galactic center could be a perfect arena for them to collide. When a particle of dark matter meets its antiparticle, the theory goes, they would annihilate each other, producing a cascade of standard particles that ultimately decay into gamma rays. The smooth, spherical shape of the excess matches what you would expect from the diffuse halo of dark matter, and its energy spectrum fits certain WIMP models beautifully. For a time, this was a thrilling prospect, a potential indirect detection of the universe's most elusive substance. The second major theory points not to new physics, but to a hidden population of ancient stellar corpses. Millisecond pulsars are neutron stars that have been spun up to incredible speeds by siphoning material from a companion star. They are faint, steady emitters of gamma rays. The galactic center is an ancient, crowded place, and astronomers suspect it could be home to tens of thousands of these faint pulsars, each one too dim to pick out individually in the Fermi data. Together, their combined glow could perfectly mimic the smooth, excess emission we see. Recent analyses have found some evidence of point-like sources within the excess, lending weight to this more conventional, though still fascinating, explanation. The debate continues, a tug-of-war between the revolutionary and the merely extraordinary. Is the glow the long-sought signature of dark matter's demise, or simply the collective whisper of countless dead stars we have yet to count? For now, the galactic center holds its secret close, radiating a question in the universe's most energetic light. That high-energy gamma-ray glow is paired with a much cooler, but no less mysterious spectral signature written in infrared light. Across the galaxy, in star-forming nebulae and the dusty disks of other galaxies, astronomers detect a series of sharp, bright emission bands at very specific infrared wavelengths. These are the unidentified infrared bands, and they are the fingerprints of complex chemistry happening in the cold darkness between the stars. The pattern is unmistakable and universal, showing up wherever there is carbon-rich dust being illuminated by starlight. The leading suspects for the molecules causing these bands are polycyclic aromatic hydrocarbons, or PAH. Picture these not as liquids or powders, but as tiny, flat flakes, miniature chicken wire mats of carbon atoms ringed with hydrogen. They are essentially microscopic pieces of soot, the same family of compounds found in car exhaust and charcoal grills. When a single photon of ultraviolet light from a nearby star strikes one of these flakes, it makes the entire molecule vibrate like a struck tuning fork, and it re-emits that energy as a specific infrared glow. The mystery is not whether PAHs exist. The chemical evidence is very strong. The puzzle is that we still cannot definitively match the observed infrared bands to specific, individual pH molecules in a laboratory. Space is a brutal environment, with these molecules being bombarded by radiation and battered by collisions. They are likely not pristine textbook examples, but a messy, complex zoo of related species, some ionized, some with irregular edges, some clinging to dust grains. Identifying the exact carriers is like trying to identify every instrument in a symphony by listening to the single, combined note they all play at once. This interstellar chemistry puzzle is profoundly important because PAHs are believed to be fundamental building blocks of probiotic chemistry. They are abundant, stable, and could have been delivered to the early Earth via comets and meteorites, providing a potential head start for the chemistry of life. So these unidentified bands are more than just a spectroscopic curiosity. They are a direct window into the complex organic chemistry that fills the galaxy, a chemistry that might well be the first step on the long road from stardust to biology. That galactic chemistry of soot and starlight operates on a scale of light years, but the universe weaves its largest patterns across distances so vast they strain the very definition of structure. Two discoveries in particular have stretched our cosmological models to the breaking point. The first is a colossus known as the Hercules Corona Borealis Great Wall. It is not a physical barrier, but a mind-bending filament of galaxies, a dense river in the cosmic web that measures over 10 billion light-years from end to end. To grasp that scale, if you could travel at the speed of light, it would take you more than twice the current age of the Earth just to cross it. Its discovery was a statistical shock. Astronomers mapping gamma-ray bursts, the most powerful explosions in the universe, noticed an alarming concentration of them in the constellations Hercules and Corona Borealis. These bursts are so luminous they act as beacons, marking the locations of distant galaxies. The pattern revealed a structure of such immense size that it should not exist, at least not according to a fundamental rule called the cosmological principle. This principle states that on the largest scales, the universe should look roughly the same in every direction and have no outstanding features. Matter should be smoothly distributed. The Hercules Corona Borealis Great Wall is a glaring exception, a cosmic continent in a universe we thought was an ocean of fine sand. The problem is not just its size, but its age. The structure is so enormous that the light from one end has not had enough time since the Big Bang to reach the other end. This means the two ends could never have been in causal contact. They could never have exchanged information or influence to coordinate their formation into a single, coherent structure. How then did this thing come to be as one connected entity? It is a paradox written across 10 billion light-years. A similar challenge comes from another monster, the Huge Large Quasar Group, or huge LQG. Quasars are the brilliant, active cores of distant galaxies, powered by supermassive black holes feasting on matter. This group is a collection of 73 quasars bound together by gravity, stretching across 4 billion light-years. Like the Great Wall, its scale seems to violate a statistical guideline known as the homogeneity scale, which predicts the maximum size for structures in the universe. Finding something this large is like rolling a pair of dice 100 times and getting snake eyes every single time. It suggests the dice might be loaded or our understanding of the game is wrong. So what do these cosmic giants mean? One possibility is that they are forcing a profound revision of cosmology itself. Perhaps dark energy or the nature of inflation in the early universe worked differently in certain regions, allowing matter to clump together on scales we thought impossible. Another, more humbling possibility is that these are not single, connected structures at all, but chance alignments of smaller filaments seen in projection, a trick of perspective that makes separate threads look like one colossal rope when viewed from our particular point in space. Or perhaps our statistical models for what constitutes a structure are simply too simplistic for the messy, complex reality of the cosmic web. These are not just curiosities for astronomers, they are stress tests for our entire picture of the universe. They ask if the smooth, uniform cosmos we believe in is truly the whole story, or if, when we pull back far enough, we might find that the universe has a grain, a texture, with features so large we are only just beginning to see their outlines. The immense scale of cosmic structures tests the limits of our cosmological models, but the very light we use to measure them holds a deeper, more fundamental mystery. The redshift of distant galaxies is the cornerstone upon which our entire picture of an expanding universe is built. When astronomers analyze the light from a far-off galaxy, they find its familiar spectral lines. The chemical fingerprints of elements like hydrogen and helium are all shifted toward the red end of the spectrum. In the standard cosmological model, this is not because the light itself is changing color, but because the very fabric of space through which it travels is stretching. As a light wave journeys across billions of light-years, the expansion of the universe literally lengthens its wavelength, stretching it from blue toward red. This cosmological redshift is a direct measure of both distance and cosmic history. The farther away a galaxy is, the faster it appears to be receding from us, a relationship encoded in Hubble's law. It is the reason we speak of a Big Bang, an initial moment from which everything has been flying apart for 13.8 billion years. Yet, from the very beginning, this interpretation has faced challenges. One of the most persistent, though now largely discarded, alternatives is the tired light hypothesis. Proposed shortly after Edwin Hubble's discovery, it asked a simple, radical question: what if the universe is not expanding at all? What if redshift is not a Doppler-like effect of space stretching, but a sign that light itself grows weary on its epic journey? In this view, photons of light would gradually lose energy as they travel across the vast intergalactic gulfs, perhaps by interacting with a faint, diffuse medium or through some unknown intrinsic process. Losing energy means increasing wavelength, which we would observe as a redshift. This was an elegant idea, as it could explain the observed redshift without requiring the universe to have a beginning or to be dynamically evolving. It presented a static, eternal cosmos, which many found philosophically more comfortable than a universe with a definitive start. So why did this idea fall out of favor? The evidence against it is overwhelming and comes from multiple, independent lines of observation that all point unequivocally to an expanding, evolving universe. First, if light simply tired due to interactions, that interaction would also scatter the light, blurring the images of distant galaxies and quasars. We see no such blurring. Distant objects appear sharp and clear. Second, and decisively, we observe a phenomenon called time dilation in the light curves of distant supernovae. In an expanding universe, time itself is stretched along with space. A supernova explosion in a far-off galaxy should appear to unfold more slowly from our perspective, its brightening and fading stretched over a longer period. This is exactly what we see. In a static universe with tired light, no such time dilation would occur. The supernova's light curve would appear compressed and sped up, which it does not. Finally, the entire thermal history of the universe, culminating in the perfect blackbody spectrum of the cosmic microwave background radiation, is a natural prediction of an expanding, cooling fireball. A static universe offers no coherent explanation for this pervasive, cool glow. The consensus for cosmic expansion is not built on a single observation, but on a convergent web of evidence where redshift, time dilation, and background radiation all tell the same, consistent story of a cosmos that has grown from a hot, dense state. The tired light theory remains a fascinating footnote, a reminder that even our most bedrock ideas must withstand the test of every new and clever way the universe finds to reveal its truths. Our cosmic inventory has long suffered from a glaring accounting error. We know precisely how much ordinary matter, the protons and neutrons we call baryons, should exist in the universe. The recipe is written in the light of the Big Bang's afterglow, the cosmic microwave background. That ancient light tells us that baryonic matter should make up about 5% of the total cosmic budget. Yet, when astronomers added up all the visible matter, every star, every galaxy, every dust cloud they could see, they came up short, dramatically short. About half of all the normal matter in the universe was simply missing. It was as if you carefully budgeted for a grand construction project, but when you went to the warehouse, half the bricks were gone. This was the missing baryon problem, and for decades it haunted cosmology. Where could half the universe's normal stuff be hiding? The answer, it turns out, was not in some distant, dark corner, but in the very space between the galaxies, in a form so diffuse and energetic it had escaped our notice. Astronomers call this hidden reservoir the circumgalactic medium, a vast, hot halo of gas that envelops galaxies like ours, and beyond that, an even more tenuous web known as the warm-hot intergalactic medium, or the WIM. This is not the cold, dark vacuum of space we imagine. It is a seething, million-degree soup of ionized gas, so hot that its atoms are stripped of their electrons, making it completely invisible to optical telescopes. To find it, scientists had to change how they looked. They turned to space-based observatories that see in ultraviolet and X-ray light, like the Hubble Space Telescope and the Chandra X-ray Observatory. Their strategy was ingenious. Instead of trying to see the hot gas directly, which is nearly impossible, they used distant beacons as cosmic flashlights. When the brilliant light of a distant quasar travels across billions of light years to reach us, it passes through these invisible filaments of hot gas. The specific atoms in that gas, even when ionized, can absorb very particular wavelengths of that background light. As the quasar's light journeys through the WIM, it picks up a series of faint, specific absorption lines like a spectral barcode imprinted on it. By analyzing the precise fingerprints of elements like oxygen and neon in the quasar's ultraviolet and X-ray spectrum, astronomers can detect the presence, temperature, and density of this elusive material. It is detective work on a cosmic scale, reading the shadow of a ghost by the light it steals. What they found completed the ledger. This hot, diffuse gas, strung along the cosmic web's filaments and pooled in galactic halos, accounts for the missing 50%. It is the universe's normal matter, not lost but transformed into a state we could not see. This discovery closes a fundamental chapter in cosmology, but it opens a new one on galactic life cycles. This circumgalactic medium is not a passive reservoir, it is a dynamic engine. It is the source of fuel for future star formation, a galactic fountain where supernova explosions eject material out into the halo, only for it to cool and rain back down onto the galaxy, seeding new generations of stars. We are finally seeing the full ecosystem of a galaxy, not just the shining cities of stars, but the invisible, cycling atmosphere that sustains them. The universe's normal matter was never truly missing. We were just looking for stones and missing the steam. That hidden, seething atmosphere of hot gas is the fuel for galaxies today, but the cosmic engine driving it all has a final destination. Our journey through 50 galactic mysteries leads us to the ultimate question: how will it all end? The universe's final fate is not written in stone, but in the subtle balance between its expansion, its matter, and the phantom force of dark energy. Cosmologists have outlined three primary scenarios for the grand cosmic finale, each dictated by the density of the universe and the nature of dark energy. The first, and currently the most supported by observations, is the Big Freeze, also known as heat death. In this scenario, dark energy continues to dominate, driving the accelerated expansion of space forever. Galaxies will be pushed beyond each other's cosmic horizons, their light forever lost to one another. Within each isolated galaxy, star formation will eventually cease as gas is locked away in dead stars or expelled into the void. Over trillions of years, the last stars will flicker out, leaving the cosmos to the cooling embers of white dwarfs, neutron stars, and black holes. Even these remnants are not eternal. Through a process called proton decay, if it occurs, the very atoms of dead stars may eventually dissolve into subatomic particles. And in timelines so vast they defy comprehension, even black holes will evaporate via Hawking radiation, releasing their final whispers of energy into an ever colder, darker, and more uniform void. This is the state of maximum entropy, where no energy gradient remains to do any work, and the universe achieves a silent, eternal equilibrium. It is a profoundly cold and lonely end. The second possibility is far more violent: the Big Rip. This scenario arises if dark energy is not constant but grows stronger over time, a form known as phantom energy. In this future, the repulsive force of dark energy would eventually overcome every binding force in nature. First, galaxy clusters would be torn apart, then individual galaxies. As the acceleration becomes infinite, stars would be ripped from their orbits, planets from their stars. In the final moments, the phantom force would overcome the forces holding atoms together. Then the nuclear forces within atomic nuclei, shredding all matter into its fundamental particles in a catastrophic, universe-wide instant. The third, and now largely disfavored, scenario is the Big Crunch. This would require the density of matter in the universe to be high enough that gravity eventually halts and reverses the expansion. Everything would begin rushing back together, galaxies merging in a reverse of the Big Bang, temperatures and densities soaring until the entire observable universe is compressed back into a singularity, a hot, dense point that might then give birth to a new universe in a cyclical cosmic rebirth. Current evidence strongly points away from this fate. Measurements of the cosmic microwave background, the distribution of galaxies, and the acceleration driven by dark energy all indicate a universe that is not dense enough to ever collapse back on itself. The expansion appears to be permanent and accelerating, so the leading model, the one our telescopes support, is the Big Freeze. It is a finale not of fire but of ice, a slow fading of all light, structure, and complexity into a timeless, uniform dark. This cosmic destiny is humbling, placing our vibrant, temporary universe within a narrative of unimaginable scale, where even the mightiest galaxies are but brief sparks in eternal night. And there you have it, 50 galactic phenomena that stretch the limits of our understanding and imagination. From the ghostly pull of dark matter to the silent question of the Fermi paradox, the universe is far stranger and more wonderful than we often dare to dream. These mysteries are not dead ends, they are invitations. Invitations to observe, to question, and to explore. They remind us that science is not a dusty collection of answers, but a living, breathing conversation with the cosmos. A conversation where every solved puzzle reveals two new, more fascinating questions. So keep looking up, keep wondering. Let the strange silence of the cosmos and the brilliant violence of its stars fill you with that essential human spark, curiosity. Who knows, maybe one day you'll be the one to look at a day, to plot or a star chart and see the clue that unravels one of these cosmic puzzles. If you enjoyed this journey through the unexplained, smash that like button, subscribe for more deep dives into the unknown, and tell us in the comments which phenomenon blew your mind the most. Until next time,